Hello, Sauce here. We're going to talk a little bit more about average rate of change. This lesson comes after the lesson on general expression for average rate of change. The reason why we're spending so much time with this concept is that it's going to lead into calculus very soon. So what can we say about average rate of change? How can we develop this idea a little further? I'm going to sketch a graph to visualize what we've been talking about. I'm going to sketch a generic curve. This could be any function. And I'm going to make a choice. My horizontal variable is going to be t. We're going to imagine t maybe time. And the vertical variable will be p. Maybe p stands for position. So if this is a graph of the position of something, it should be obvious that the position is changing over time. It looks like the position of something is going up as time goes on. And so when we talk about the average rate of change, we're thinking about the rate at which the position is going up. And that concept is called velocity. Again, if I put a point on my graph, I could imagine that the point represents a position, a specific location, and if that location changes, if it goes up, it will be in a new position, but it will take time to get there. And the rate at which the position changed to go from one place to another position would be the velocity of that thing. Let's put a little more detail into our graph. I'm going to imagine that the position at this point started at time 3. And if time went on, then I could put a tick mark at the time at which the position was represented by this dot. But rather than choose another value here, I'm going to think about the quantity of change from 3 to this new location as a variable amount of time, and I'm going to give that amount of time the variable h. So this tick mark would be the initial time of 3 plus the amount of time h. If I wanted to focus on the full coordinates of these points, then I could label this tick mark as the p function evaluated at time 3. And this tick mark here that represented this position would be the p function evaluated at 3 plus h. Here's a graph presentation. How are we going to think about it as an equation that we could use to calculate an average rate of change? Average rate of change can be abbreviated. It ought to be. Spelling it out is quite tedious. AROC, or we could say AROC. And AROC is a slope calculation. Instead of change in y over change in x, since I've chosen my variables here, that slope calculation is going to be change in p divided by change in t. It's the amount that the position goes up as time increases. And as we talked about before, this is a velocity calculation if my graph is in the context of the position of something changing. Okay? And in this calculation, we could do a little bit further, we could go a little further, because the change in p, given these labels, can be a little bit more precise. It is the latter p-value minus the initial p-value, or p evaluated at 3 plus h minus p of 3. Again, that's how we can represent change in p given these labels and information. And we're going to divide now by change in time, or delta t. In this presentation, we did something a little bit more useful. Delta t was given this variable h. If we start at 3 and we go to 3 plus h, the amount of change of my horizontal variable t is just represented by that single variable h, making this presentation very efficient. This presentation here will calculate the velocity of something that is changing according to the p function. But we don't have the p function, we don't have an expression for it. We can get a little bit more general than this. If instead of a position function, we wanted to think of any generic function f, and if instead of a very specific initial value of 3, we wanted to think more generally like a starting value or initial value of a, then the AROC expression could be represented as the function evaluated at a ladder value, that's the initial plus the change, minus the function evaluated at the initial point, all over h. This here is the general average rate of change function, or expression to evaluate the average rate of change. And in this presentation, the horizontal change is given by a single variable h. Let's use it. We could be given a function, problem, and it's going to take me a moment to write it down. What is the average velocity of a rocket whose position in feet is given by a function, position as a function of time equal to t squared, from double inequality for t from t 0 to 3 seconds. That's a question. Let's take a moment to understand the question in the context. We have a rocket. It is taking off. It starts at an initial time of 0. We're given a position or a height function for the rocket. And after 3 seconds, the position of the rocket is going to go up. It's going to start to take off. 3 seconds is not much time. It will not reach a very high position, but we're asked to find the velocity or the rate at which the position is changing on average in this interval of time. This is an average rate of change question in the context of position and time. So we're going to be calculating a velocity. And here's what we need to know to be able to use this expression. We need a function. We have it. It's the p function. We need an initial value in the domain. We have it. It's 0. And we need h, the amount of change in the horizontal variable. We have it. It's 3. The amount of change from 0 to 3 is 3. So we have an a value of 0, an h value of 3, and we have our position function. So we're going to calculate the average rate of change. In this context is a velocity. And that velocity will be the p function evaluated at the initial time plus the change minus the p function evaluated at the initial time divided by the amount of change. Let's do a little bit more work. The p function evaluated at 0 plus 3 is the same thing as putting 3 in for t into our p function, and 3 squared is 9. Minus the p function evaluated at 0, 0 squared is 0. And we're going to divide by h, the amount of change in time, which is 3. Simplifying this, 9 minus 0 is 9, divided by 3 is 3. And this is a contextual question, so it's going to be a velocity in feet per second. 3 feet per second is the average velocity of the rocket taking off. Not very fast, but if something is very heavy, it's going to go slow real soon after takeoff.